Now let us solve the problem on the formula of integrated rate law for the solutions. Now see this problem 6.8. It is as the half-life of the first order reaction is 990 seconds. This is the half-life of the first order reaction, 990 seconds. If the initial concentration of the reactant is 0.08 moles per decimeter cube, initial concentration of reactant is 0.08 moles per decimeter cube, what concentration would remains after 35 minutes? That means we have to calculate 80. After 35 minutes, we have to calculate the 80 concentration of the reactor after 35 minutes. And we have given the initial concentration A0 at 0.08 moles per decimeter cube. Let us see what is given. The half-life period is given, that is equal to 990 seconds. Again, the initial concentration is also given, that is equal to 0.8 moles per decimeter cube. Then the time is given 35 minutes. As the time half-life period is in seconds, so convert this time also in second by multiplying 60, because 60 seconds is equal to 1 minute. So 35 into 60, that becomes 2100 seconds. Now 80 we have to calculate, but in our formula there is the rate constant K is also. So first calculate the rate constant K from this half-life period, because the relation between the rate constant and half-life period is equal to K is equal to 0.693 divided by T half. So we have to first calculate the rate constant K by this formula. K is equal to 0.693 divided by T half. Here T half is the 990 second. So 0.693 divided by 990 second, that becomes 0.0007 per second. And this is equal to K is equal to 7 into 10 raised to minus 4 per second, because this that is the decimal goes here. So it becomes 7 into 10 raised to minus 4 per second. Now this is the value of K. Now our integrated rate law for the first order reaction is given as K is equal to 2.303 divided by T log to the base 10 A0 divided by 80. Now substitute all the values. First we have to calculate this 80. So this quantity suppose remains here. Then this T is multiplied to this K, and this 2.303 get divides. So log to the base 10 of A0 divided by 80 is equal to K into T divided by 2.303. The value of K is 7 into 10 raised to minus 4 per second, and the time T in second is 2100 second. Now this per second and second, the unit gets cancelled and divided by this 2.303, that becomes the log of A0 upon 80 is equal to 0.6383. Now this is the value, but we have to calculate the 80. So after taking antilog to both sides, we can calculate the value of 80. Now see this. Now see, log to the base 10 of A0 divided by 80 is equal to 0.6383. Now this is the value of this. Now by taking antilog to both sides, this becomes concentration of A, that is the A0 initial concentration divided by 80 concentration after time T is equal to antilog of this, that is the value 0.6383. The antilog of 0.6383 is 4.35. So A0 divided by 80 is equal to 4.35. Now we have to calculate this 80. So 80 is equal to A0 divided by 4.35. The A0 is 0.08 moles per decimeter cube. That is the initial concentration of A. So 0.08 moles per decimeter cube divided by 4.35, that is equal to 0.0184 moles per decimeter cube. That concentration will be remains after 35 minutes. Now see the problem. Now let us see problem 6.9 now. Now this is the problem number 6.9. Now this is also very simple problem and very easy. Now in the first order reaction, 60% of the reactant decomposes in 45 minutes. That means 60% of the reactant gets, that is used. That is it gets decomposed or it gets consumed, 60%. Suppose initially the reactant is 100%. Out of that, 60% reactant get decomposed. So how many reactant remains? 100 minus 60, that is equal to 40%. And we have to calculate here, calculate the half-life of the reaction. Now see what are given. The initial concentration, suppose it is the 100% because the concentrations are given in percentage. Out of that, after 45 minutes, 60% reactant gets consumed. So 80, that is the at time t, the concentration of A is 100 minus 60. Now what is remaining? Only the 40% of the reactant is remaining. And time is given 45 minutes. We have to calculate the half-life period. But for half-life period, first calculate the K, that is the rate constant. So our formula is, from the formula, K is equal to 2.303 divided by T log to the base 10 A0 upon 80. Now that is 2.303, time is 45 minutes, log to the base 10, 100 divided by 40. Now this is the initial concentration, this is the concentration after time T. So 2.303 divided by 45 minutes, log of, now this becomes, now this cancelled, 0, 0, 4, 1 ja 4, 4 2 ja 8, what is remaining? 2 and 4 panja, that is the that is 20. Now this is the 2.5 here. So log of 2.5 is 0.3979, and after calculation of this, we obtain the value of K is equal to 0.0204 per minute. Now this is the value of K. Now that is easy to calculate the half-life period. So half-life period T half is equal to 0.693 divided by K. That is equal to 0.693 divided by 0.0204 minutes, and T half is equal to 34 minutes. Now in this way we can calculate the half-life period also, the rate constant, or we can calculate the concentration after time T by these two formulas. That is the K is equal to 2.303 divided by T log to the base 10 A0 by 80, and the another formula that is very important, T half is equal to 0.693 divided by K. Now let us calculate problem number 6.10. What is that problem? Now this problem is on the integrated rate law for the gas phase reactions. Now see, following data were obtained during first order decomposition of SO2Cl2 at the constant volume. Now the reaction is SO2Cl2 gas gives SO2 gas plus Cl2 gas. Now time in second is given. Initially when the time T is equal to 0, the initial pressure, total pressure in bar is 0.5, that is the initial pressure PR. And after 100 seconds, the pressure becomes 0.6 bar. So the pressure P is equal to 0.6 bar here. That is after 100 seconds, T is equal to 100 seconds here. So after 100 seconds, P is equal to 0.6 bar. That is the pressure of the reactant mixture, and the initial pressure of the reactant is Pi is equal to 0.5 bar, and time is T in second, that is the 100 seconds. So they ask us to calculate the rate constant K for the reaction. Now our formula for integrated rate law of the gas phase reaction is K is equal to 2.303 divided by T log to the base 10 Pi divided by twice Pi minus P. Now this is the integrated rate law for the gas phase reaction. So substitute the values of Pi and P in this equation and time T. So K is equal to 2.303 divided by 100 second log to the base 10. Pi is 0.5 bar divided by 2 into 0.5 bar minus 0.6 bar. Now this becomes that is the this becomes 1.0 bar, and 1.0 bar minus 0.46 bar is equal to 0.4. So 2.303 divided by 100 second log of 0.5 divided by 0.4, because bar, that is the unit, get cancelled. And if we calculate this, after calculating this log and after this calculation, that is the rate constant obtained is 2.23 into 10 to minus 3 per second. Now this is the problem on the integrated rate law of the gas phase reaction. In this way, we can calculate that is the rate constant or half-life period or the concentration after time t by using these different formulas. Now if you that is understand this, that is the topic, then like, share and subscribe this video. Thank you.